Hello and welcome to my talk for the Junior Mathematician Research Archive. My name is Tobias Lenz. I'm a PhD student of Stefan Schwede at the University of Bonn and the Max Planck Institute for Mathematics. And today I want to give you an introduction to some of the research I did for my thesis. And in particular, I want to tell you something about equivariant, global, and ultimately G-global generalizations of algebraic K-theory. So to get things started, let me recall the classical non-equivariant algebraic K-theory of rings, and in particular the construction of the zeroth K group. For this, we let R be any ring, and we look at the isomorphism classes of finitely generated projective left R modules. These actually form a commutative monoid with monoid structure induced by the direct sum of left R modules, and we can pass to the group completion of this monoid. So the initial example of an abelian group together with a homomorphism from it. And this group is then what's usually called K0 of R. So let me give you some examples. So K0 always receives a map from the integers, which is induced by the map sending a non-negative integer n to the class of the free R module R to the n. And if our ring is a principal ideal domain, then this map will actually be an isomorphism. In general, however, K0 can be much larger. For example, if G is a finite group, then basic representation theory tells us that K0 of the complex group algebra is free abelian with basis the isomorphism classes of irreducible complex G representations. So while these two examples almost looked like K0 might be easy to grasp, this already changes quite dramatically when we pass from the complex group algebra to just the group ring, where K0 is largely mysterious even for finite cyclic G. So depending on your perspective, this example is either really bad or really exciting, because interesting topological obstructions live in K0 of the group ring, or more precisely, the co-kernel of the map from the integers to K0 that I just described. And as a final example, I want to mention, if we have any number field, so a finite extension of the rationals, then we can look at its ring of integers. And the K0 of this can be shown to split as a product of a copy of the integers and the class group of our field. So the class group is always finite, in particular torsion, but in general it's non-trivial and it's an interesting group that we want to know more about. So hopefully already these few examples hint at two things. Firstly, K-theory contains a lot of interesting information, and in fact information about a wide range of phenomena, number theoretic, topological, representation theoretic, for example. But secondly, it's really hard to compute. But this is only the beginning. So people also knew definitions of K1 and K2 that interacted nicely with K0, for example, through some exact sequences. So naturally, they looked for definitions of K3 and K4 and so on. And this was then finally achieved by Quillen, who gave two equivalent constructions of higher K groups, one the so-called Q construction and the other one based on the plus construction. But while K0, as we have just seen, and also K1 and K2 can be defined in purely algebraic terms, Quillen's construction is now homotopy theoretic. Namely, he first builds a space K of R, and the K groups are then just the homotopy groups of this space. In fact, K of R is not just any space, as evidenced, for example, by the fact that K0 is a group, but it comes with extra structure naturally that makes it into an infinite loop space, or equivalently into a connective spectrum. And this spectrum will be the object we are actually interested in today. Moreover, as a nice side effect of the Q construction, it became crystal clear that K-theory does not really depend on the ring R itself, but only on the category of R modules, and in fact only on the category of finitely generated projective left R modules. And based on these two observations, there have been several generalizations of K-theory that produce connective spectra from some sort of categorical input data, each capturing one aspect of the module category. And what I actually want to talk about today is the K-theory of symmetric monoidal categories, and in particular, one construction of it due to Siegel and Shimada and Shimakawa. Here, the prototypical example is the category of finitely generated projective R modules and R linear isomorphisms, with symmetric monoidal structure given by direct sum again, so the coproduct in the ambient category. Basically, by design, we want that the K-theory of these categories recover the K-theory of rings which were just defined, But of course, there are now much more examples of symmetric monoidal categories than just module categories. And once this whole theory is set up, for example, the famous Barrett-Pretty-Quillen theorem will tell us that the K-theory of finite sets and bijections under disjoint union is just a sphere spectrum. So before I say something about the construction, I want to give you a slogan because I think this is enlightening, and this is also the perspective that I want to take later for equivariant and global algebraic K-theory. And this slogan says that K-theory is higher group completion. So to explain this, let me first tell you how we can define K0 of a symmetric monoidal category in analogy with the construction for rings. Namely, we can look at the set of components of the nerve of C, and this again becomes a commutative monoid under this monoid structure induced by the tensor product on C. And we can simply take K0 to be the group completion of this. Note that if C is the category P of R just defined, then this is literally the same as the previous construction of K0 of R. But of course, we throw away a lot of information when we pass from the symmetric monoidal category C to just the commutative monoid pi0 of C. And we can think of this, the tensor product, and the symmetry isomorphisms and associativity isomorphisms and so on, as equipping C with the structure of a commutative monoid up to coherent homotopy. And we may want to try to group complete this thing. But of course, to talk about this vigorously, we first have to make precise what such a coherently commutative monoid should be. And one of several equivalent approaches to this is Siegel's theory of gamma spaces. Here, gamma is just the category of finite pointed sets and based maps, which in particular has a skeleton given by the objects usually denoted by n+, which is the set of integers from 0 to n with base point 0. A gamma space is simply a functor from gamma into a favorite category of spaces, which will always be simplicial sets for me today, such that x evaluated at 0 plus is just a terminal space. So there are several interesting maps that we can construct from this structure. Firstly, if we have any non-base point of I of n+, then we get a map from n+ to 1+ by projecting away from this element. So we send everything else to the base point and we send I to 1. And for varying I, these maps assemble into the so-called Siegel map, which goes from x evaluated at n+ to the n-fold product of x1+ with itself. On the other hand, we can just look at the map that sends every known base point to 1, which induces a map from x evaluated at n+ to x evaluated at n at 1+. And what we usually want to do is we want to think of x evaluated at 1+ as the underlying space of our gamma space, and as these maps are some sort of higher multiplications on this space. But for this intuition to make sense, we need an additional condition on our gamma space, and this is what's usually called specialness. Namely, we want that all these Siegel maps are weak equivalences. So note that this in particular gives us a map in the homotopy category from the n-fold product of the underlying space with itself to the underlying space. And we can now really think of these as sending an n-tuple x1 to xn to the product x1, x2, and so on to xn. But of course, we have more structure because we do not pass to the homotopy category beforehand. So here are some examples again. Firstly, gamma spaces really generalize strictly commutative monoids in the following sense. If we have any commutative simplicial monoid, then we can build a gamma space from this which sends n+ to the n-fold product of our monoid with itself, and all structure maps are given by summation over the fibers. It's then trivial to check that in this case the Siegel maps are even isomorphisms, and in fact one can show that this construction provides an equivalence of categories between simplicial commutative monoids on the one hand and gamma spaces such that the Siegel maps are isomorphisms on the other hand. But of course, we do not require the Siegel maps to be isomorphisms, but only weak equivalences. And we should think of this extra flexibility as allowing us to sneak in all these coherence data without ever having to talk about them explicitly. And of course, we get new examples this way. And for example, Shimada and Shimakawa have shown how any symmetric monoidal category gives rise to a special gamma space. So what does this buy us? So once we have a gamma space, we can deloop it to get a connective spectrum. And Siegel has shown how we can think of this delooping construction as a group completion in the following sense. Namely, it has the same formal properties as ordinary group completion. Ordinary group completion is left adjoint to the inclusion of commutative groups into commutative monoids. And likewise, Siegel showed that the still looping functor is left adjoint to a certain functor from connective spectra to gamma spaces that is an equivalence onto the group-like or very special gamma spaces inside the special gamma spaces. So note that neither for the delooping construction nor for Siegel's theorem, we actually need to restrict to special gamma spaces beforehand, but it will be more useful to think about special gamma spaces later. So let's just forget about non-special gamma spaces from now on. So using this, we can now simply define K-theory as the composition of first applying the Shimada-Shimakawa construction to get from symmetric monoidal categories to special gamma spaces, and then applying the delooping construction to get to connective spectra. By Siegel's theorem, we have a precise sense in which this delooping is given by higher group completion. So once you believe that gamma is the correct way to associate a special gamma space to a symmetric monoidal category, you can use this as justification that K-theory is higher group completion. But in fact, we do not have to just believe this, and the situation is even better. Namely, Mendel proved that if we look at symmetric monoidal categories, not through the eyes of symmetric monoidal equivalences, but through those symmetric monoidal functors that induce weak equivalences on nerves, then this functor becomes an equivalence of associated infinity categories. In particular, we see that K-theory is group completion in the following sense. We start with a model of coherently commutative monoids, and we end with a model of coherently commutative groups. And what happens in between is left adjoint to a functor that deserves to be called the inclusion of groups. As an immediate consequence of this, we get the following result, which is actually older and due to Thomason, that K-theory is an infinity categorical localization from the 1 or 2 category of symmetric monoidal categories to the infinity category of connective spectra. So in particular, while this is much stronger, we see that all connective spectra arise as K-theory spectra of symmetric monoidal categories. So in a sense, the K-theory of symmetric monoidal categories is as complicated as it gets. Everything can happen. But this does not mean that we do not want to make things even more complicated by introducing more structure. And one way to do this that I find particularly interesting is equivariant algebraic K-theory. Here, the basic observation is that many inputs we care about actually carry additional symmetries in the form of an action of a group, which we, for technical reasons, have to require to be finite. As a concrete instance of this, if you have any finite Galois extension, then of course the larger field carries an action of the Galois group. While we can now just use the ordinary non-equivariant K-theory construction and equip this K-theory spectrum with the induced action, there is actually a richer structure we might hope for, namely a genuine G-spectrum in the sense of equivariant stable homotopy theory. This differs from the naive notion of a G-object in the infinity category of spectra in basically 2 ways. First, we have genuine fixed point spectra for all subgroups, and these are usually different from the homotopy fixed points. And secondly, we do not just encode deloopings against the ordinary spheres as 1, as 2, and so on, but in fact against all representation spheres. So against all one-point compactifications of finite dimensional orthogonal G representations. And as a concrete consequence of these 2 facts, genuine G-spectrum has not just a single homotopy group in each dimension, but in fact one such homotopy group for each subgroup of G, and there are natural structure maps between them, namely conjugation homomorphisms, restriction maps, and transfer maps, which then give them the structure of a so-called Mackey functor. And in particular, if we manage to construct equivariant K-theory as a genuine G-spectrum, we will not just get a single K-group in each dimension, but a whole Mackey functor of K-groups, which is of course much more structured than just the non-equivariant K-group with induced action. But this also means that constructing such a genuine G-spectrum won't come for free as a consequence of the functoriality of non-equivariant K-theory, and instead there is still some work to do. But fortunately, there are people who did this work for us, and in particular Shimakawa on the one hand, provided a G-equivariant generalization of Segal's gamma space theory, and on the other hand, he showed how a symmetric monoidal category with G action gives rise to such a coherently commutative G-equivariant monoid. So note that already this passage is more subtle than one might guess, and I will say something about this later. So instead of going into Shimakawa's construction, I want to give you some examples of this. Firstly, if we return to our motivation of a finite Galois extension, then, as we might guess, the underlying non-equivariant spectrum of our G-equivariant K-series spectrum is just the ordinary non-equivariant K-series spectrum of the total field. But what happens now is that the G fixed points of this recover the K-series of the base field. On the other hand, it turns out that equivariant K-series is even interesting when we only consider trivial G actions. And for example, if we have any Q algebra R, then the H fixed points of the equivariant K-series of R as equipped with a trivial action recovers the K-series of the group algebra with coefficients in R for any finite group H. And in general, if you have any symmetric monoidal category C, then the H fixed point of the equivariant K-series of C with trivial G action recovers the ordinary K-series of H objects in C. This leads to the following question. So if you just fix a symmetric monoidal category C, then we can equip it with a trivial G action for all finite groups G. And so we get for each finite group G a genuine G spectrum. And as one might expect, for varying G, these G spectra are not just independent of each other, but they are again suitably related. And so we might want to package all this information into a single object. Of course, to make this precise, we first have to say what we mean by such a compatible family of genuine G spectra for varying G. And one rigorous framework to talk about is this global stable homotopy theory. And in fact, recently, using this framework, Schwede proposed a construction of global algebraic K-theory, which then associates a global spectrum to a symmetric monoidal category. Such a global spectrum has an underlying G spectrum for any finite group G, and in particular, it has an H fixed point spectrum for any finite group H. And one can show that Schwede's global algebraic K-theory recovers equivariant K-theory with respect to trivial actions in the following sense. The underlying G spectrum of the global K-theory of C is just the equivariant K-theory of C equipped with a trivial G action for any group G. And in particular, we see that the H fixed points of Schwede's global K-theory recover the ordinary K-theory of H objects in C. And the collection of all these K groups for varying H together has been studied before, and it's sometimes called sworn K-theory. If you now want to compare G-equivariant and global algebraic K-theory to each other, you might notice that they actually are generalizations of non-equivariant algebraic K-theory into two different directions, and that they are not immediately comparable. In particular, global algebraic K-theory takes less general inputs, but it produces more structure on the output. And while we have just seen that these two constructions are suitably compatible with each other, this is not really as strong a statement as one might want. For example, it does not tell us anything about the G-equivariant algebraic K-theory for symmetric monoidal G categories with non-trivial actions. Instead, I want to suggest to think of both of these constructions as aspects of a more general construction, which I call G-global algebraic K-theory. In order to talk about this, we of course first have to make precise where this should live, and this leads to the notion of G-global stable homotopy theory. This is actually an idea that has been around for some time, but which had not been developed systematically before. As a design principle, such a G-global spectrum has a genuine fixed point spectrum for any homomorphism from a finite group to G. In particular, if G is a trivial group, then the datum of such a homomorphism is just the same as the datum of this finite group. So one global spectrum again has fixed point spectra for all finite groups. And in fact, basically by design, one global spectrum is the same as a global spectrum. However, for general G, something new and interesting happens now. Namely, there is an explicit and canonical way to exhibit G-equivariant stable homotopy theory as a Gauss-field localization of G-global stable homotopy theory. Note that this is different from the relation between global and G-equivariant stable homotopy theory. Namely, while any global spectrum has an underlying G-spectrum for any group G, this functor is usually not a Gauss-field localization, and in fact, it's not even essentially surjective. So using this new framework, I was then able to construct G-global algebraic K-theory, which, as you might guess at this point, constructs G-global connective spectra from symmetric monoidal categories with G-action. This indeed generalizes the previous two constructions in the following sense. One global algebraic K-theory again recovers global algebraic K-theory, and for general G, if we apply the forgetful functor from G-global to G-equivariant stable homotopy theory, we precisely get back the G-equivariant algebraic K-theory spectrum. Basically, by design, G-global algebraic K-theory is compatible with restriction along arbitrary group homomorphisms. And together with these two comparisons, this already immediately implies the relation between G-equivariant and global algebraic K-theory we had before. And because of this, I want to suggest to think of the existence of G-global algebraic K-theory in itself as a comparison or compatibility between G-equivariant and global algebraic K-theory. Finally, I want to give you an application of the theory and go back to the slogan we had in the beginning, that non-equivariant K-theory is higher group completion, which gives us a very conceptual description. In contrast to this, global and G-equivariant algebraic K-theory are just defined in terms of concrete constructions. And while these constructions are, of course, motivated by the non-equivariant one, it's not at all clear why these should be the correct generalizations. However, as the main result of my thesis, I was able to prove the following generalization of Mendel's and Thomason's results. If we look at the G-global algebraic K-theory functor as a functor from the 1 or 2 category of symmetric monoidal categories with G-actions to the infinity category of connective G-global spectra, then it's infinity categorical localization, so generalizing Thomason's results. And in fact, if we look at the symmetric monoidal G categories through the eyes of a certain explicit but slightly subtle notion of weak equivalences that I call G-global weak equivalences, then the intermediate passage to a certain notion of special G-global gamma spaces is again equivalence of associated infinity categories, generalizing Mendel's result. And indeed, with respect to this notion of weak equivalence, the G-global algebraic K-theory functor will again be a Gauss-field localization. By all the compatibilities we discussed above, this theorem in particular immediately implies the corresponding statements for G-equivariant and global algebraic K-theory. So the global statement had been a conjecture by Schwede, and as far as I know, also the G-equivariant statement had not been proven before. Note that this in particular, by the same arguments as in the non-equivariant situation, allows us to give rigorous meaning to the slogans that G-equivariant global and G-global algebraic K-theory are given by a G-equivariant global and G-global higher group completions, respectively. Moreover, we in particular see that all connective G-equivariant global or G-global spectra arise via this K-theory construction. This is particularly interesting in the equivariant situation because these symmetric monoidal categories with G-action we consider all the time are sometimes called naive symmetric monoidal G categories to distinguish them from a certain notion of genuine symmetric monoidal G categories. Shimakawa's equivariant K-theory construction actually factors through a strictification procedure from naive to genuine symmetric monoidal G categories. But this theorem tells us that nevertheless, the naive symmetric monoidal G categories still account for all connective G-equivariant stable homotopy types. And in fact, also for all special G-equivariant gamma spaces. So while I of course can't go into details about the proof here, I at least want to give you some overview of the general strategy. So for this, I drew this huge diagram here, where on the very left we have our input, and on the very right we have our output. And in fact, this horizontal composite is one of two equivalent constructions I gave for G-global algebraic K-theory. These three categories in the middle here all want to be models of G-globally coherently commutative monoids. In particular, the G-alto-commutative monoids are a generalization of Schwede's alto-commutative monoids, which are his model for coherent commutativity in the global world, while the special G-global gamma spaces are, of course, motivated by Shimakawa's G-equivariant special gamma spaces. One of the key steps of the proof is then to show that all these models are equivalent, which I think is already interesting from a purely equivariant or purely global point of view. And as the remaining steps, I then prove a generalization of Siegel's delooping theorem to the G-global world, which exhibits this delooping functor as a group completion. And finally, I give a comparison between these categorical models here on the left and these models of G-globally coherently commutative monoids. With this, I want to end my talk. If you want to read more about this, have a look at the two papers, which are linked in the video description. And if you have any questions about them, please feel free to contact me via email. And with this, thank you for listening.